Welcome, everyone. This is the second live Anyscale Academy event. Today's subject is reinforcement learning with RLlib. I can change this to indicate that we're now live. There we go. We can also, I also want to remind you about other events that we've got coming up and that we've had in the past. The next Ray Summit Connect will be July 8th. This is our summer sort of mini conference series. These are 1-hour events with several speakers on a particular topic. The next one, as you can see here, is going to be on reinforcement learning, so it'll be a nice follow-up to today's session. Then we'll have a follow-on tutorial event on the 22nd, and that will be on really kind of the rest of the Ray built-in libraries, RayTune, RayServe, and RayAutoscaler, and whatever else we've introduced by that point. So that'll be on the 22nd. You can find out more and register at anyscale.com/events. I'll just show you what that page looks like. Here you can see the next events. Also, we have an August event coming up on MLOps that you can register for. And then the Academy events, including today's, actually, are listed here that you can register for. And actually, if you go to our blog, you'll see posts about past events where you can see the videos, get the slides, that kind of thing. This is for both the Academy events, like the crash course that I did last month, as well as the Connect events. So check out anyscale.com/blog if you want to get that kind of past information. Okay. So about today's event, if you have questions or you run into issues, use the Q&A feature in the Zoom app. We'll be monitoring that. If for some reason your session doesn't appear to be working, we have a few backups that we can give you. Hopefully all of you received an email from our team in the last 24 hours with information about your session. There was a name in there, something like Academy user -100. If you have to report a problem, give us that information as well. That'll help us track it down. Also, feedback is welcome. You can give that to us in this channel. Like if I'm moving too fast, too slow, so you don't quite follow what's going on, or you're having problems with the Zoom app, or it appears that I've zoned out more than usual, you're welcome to comment there as well. So anyway, use the Q&A feature for feedback. Oh, and of course, ask questions as well. So I will periodically stop and check for questions and try to answer them. Anyway, there are 3 links that you should have seen in that email. The main one that you'll want to open now is the Jupyter Lab link, and we're going to do all of the training in Jupyter Lab. We'll also look at the Ray dashboard periodically, so that that's sort of like the name implies. It's the thing to see what's going on with Ray. What's taking all the compute and so forth. And then we also will use TensorBoard a little bit when we do model training. The sessions that you were given, I'll keep them online until mid-afternoon sometime, so that you can keep playing with them if you want. However, I suggest you save any work by downloading the notebooks, since they'll go away. You can get the code, though, from the Anyscale Academy GitHub account, all of the stuff that we're doing today, including the old Ray crash course and some things that are in the pipeline. You can just clone that Git repo. This is new training. I'd love to get your feedback, pro or con. We will send out a survey at the end, but I'd really appreciate you filling out. But you can also just contact us at academy@anyscale.com. And you're welcome to tweet today about the event. Good or bad, we accept honest criticism. You can use the hashtag Anyscale Academy, or mention one of our Twitter accounts, Anyscale Compute, Array Distributed. I will post this video afterwards. I showed you sort of briefly some blog posts from the past where we posted the links. So check for that later this week. In fact, we'll send the email to you with the survey link as soon as I get that video up. And once again, you can get all the code at this GitHub address. Our Anyscale account and Academy is the repo. Okay, and this is for later. So let me just go to my Jupyter Notebook view. This is probably what you saw when it first opened up. it shows you every possible conda environment that's available in this particular Amazon instance that we're using. What we care about is what's in RLlib. But first, let me just show you the overview. This is sort of the entry point for the tutorials. It has some suggestions for how to get help. There's a little intro video I did some while ago. A little bit of information about which tutorial you might pick, and then a high-level description of each of them. So last time we went through this Ray crash course. That's the intro to Ray. We talked briefly about some of the content in the advanced Ray course. This is very incomplete, but there's some material here that we didn't get to last time about Ray and how it works inside. Today we're going to be focusing on RLlib, and that's actually going to be divided into 3 sections, and we'll get as far as we can today. I'll come back to that description in a minute. As I said, we're going to work in this RLlib folder, so if you click on that and open it, you'll see another 00 notebook. That's the overview of this tutorial. Now, I want to take some time to go through this. One thing I want to mention, we allocated 2 hours for this. This is a massive subject, and there's far too much material for me to even cover in that 2 hours, even though it doesn't try to cover everything about reinforcement learning. I know it's going to be a bit of a fire hose drinking session today. I'll try to be careful about not losing you by going too fast. And we won't have a lot of time to spend on the exercises and so forth, because we'll also take a break in the middle, so you're not just listening to me drone on for 2 hours. But the way I'd like you to think about this course is, especially if you're new to reinforcement learning, to just sort of get the gist of what the key ideas are in reinforcement learning, the key challenges. I get the sense of how you would work with existing tools like the OpenAI gym environment, like RLlib in particular, to both learn and also to do real work with these tools. And then you can certainly come back and explore them at your own pace to kind of fill in the details. And this tutorial isn't complete. There's a lot of material that I still want to add over time, maybe getting into more advanced topics, but hopefully this will give you a good start to both using and understanding reinforcement learning, but also using Ray RLlib. Okay. Now, one thing about this, so there, it lists all the lessons here, and unfortunately the layout is kind of funky. I'd like them all to be on the left, but that's okay. But there's actually a learning plan at the bottom. So what we're basically going to do is go through the introductory material first, and not this 03 lesson that's like a reference list of papers, books, and so forth. In fact, while I'm on that subject, let me grab my favorite book. If you love textbooks, and you can't see this because there it goes. Now you can probably see it on the video, but Reinforcement Learning by Sutton and Bartow. This is the 2nd edition. This is a very exhaustive textbook, but if you really want to master the subject, it's hard to beat. It may not be the first place to go to learn necessarily, like this material hopefully would be that. But when you really want to get into it deeply, and I mention this in part because you'll see references to this book throughout the lessons. I keep hitting my microphone. You'll see references to this book throughout the lessons where I mentioned Sutton 2018, which was that edition. Okay, so we'll do the intro stuff. Then we'll talk about multi-arm bandits, which are sort of a simplified problem in reinforcement learning, but a great way to sort of get a handle on some of the concepts. We won't exactly go through all of these lessons, but we'll try. And then there's another section called Explore Reinforcement Learning with RLlib, and this is where we'll come back to the reinforcement learning general problem and explore some aspects with a few fun examples. I do have this thing called a learning plan here, which kind of just follows the outline I described, but the idea is to give you a sense of how to work through this material. We'll basically follow that to some degree today. We won't get through all of it, as I say, but hopefully you'll come away with it with a lot of interesting stuff. Okay, so let's get started. And in fact, I'll start at this learning plan. We're actually looking at this link, the Ray RLlib overview. As you can see, it's this file. So let's open this notebook, Introduction to Reinforcement Learning. That's with the 01 prefix. You can also see that here on the left in the browser. And this is where we'll start. Now, the way these notebooks, these lessons are written, they're designed really for self-taught, self-paced learning. So there's a lot of text here. Obviously, I don't want to just read text to you. That would be really painful to sit through. But I do want to give you the gist of what the text is telling you as we go along. So anyway, that's sort of the idea. So what is reinforcement learning? At the very high level, it's this idea that you have an agent. It could actually be multiple agents, but let's just assume it's one right now. That agent is observing an environment. It's making decisions, which means taking actions in the environment. And then it observes what changes happen in the environment and what rewards come back for that action. And then the goal is to maximize those cumulative rewards over time, by learning how to negotiate the environment. And that's really the gist of reinforcement learning. Everything else that we're going to discuss falls out of that sort of high-level picture. So the key words to remember here are things like agent and action and reward and observation and environment. And you can just come back to this picture if you forget what one of those are. Now, one of the big challenges in reinforcement learning, and one of the areas where a lot of research has gone into it over the years, is this so-called exploitation versus exploration trade-off. And it's this idea, imagine if the agent notices that if it continues to do one particular action over and over again, it always gets a really good reward every time. And that may turn out to be the optimal thing to do, but until the agent has explored other possibilities, it won't really know if that choice is maximizing the cumulative rewards. So one of the interesting trade-offs, and we'll get into this in more detail when we talk about multi-armed bandits, is how do you balance the idea of exploiting what you think is the best options right now versus exploring and hopefully discovering even better options. So we'll talk about that some as well. So an interesting thing, I was reading the first edition of that book, which was written like 20 years ago. And this would have been like 5 years ago. I just happened, I thought, this is kind of an interesting, if obscure branch of machine learning. So I got that book, I'm reading it, and all of a sudden Google or DeepMind, they were independent at the time, started publishing these amazing results where they were using reinforcement learning to play games at expert levels, like Atari games. This is Breakout on the right. And then the ultimate thing they did was actually beating the world's best Go players with this deep learning technology, deep learning combined with reinforcement learning. Go was considered like sort of this holy grail because apparently the state space is vastly bigger than chess. Most of us in the West think of chess as a really hard game, to become expert at, either in a machine way or in a human way. But Go was actually a lot harder, and yet they succeeded in doing this. So it was a major validation of the concept of reinforcement learning, and it drove a lot of further interest in it. And you can see some of the other examples I put here, like training these simulated environments, with this human walker, training robots to pick and place things, to do activities autonomously that as humans we take for granted that you could like pick up a book and move it or whatever, but to actually do that with a robot is non-trivial. We all hope to be driving cars like this, or actually not driving cars like this someday, where the car does the driving for us. And of course, we've used reinforcement learning to train robots to stumble down flights of stairs. So just an amazing amount of cool stuff. But if you're sitting, at home or probably not in an office, and you're thinking about, well, how do I apply this to my, real world business problems? Well, there's been a lot of cool developments here as well. And I think I get into those in a later lesson. Sorry for kind of jumping around. But there are a few of them listed here. Like, for example, there's some interesting applications to optimizing business processes, whether they're factory floors or assembly lines of various kinds, or like chemical factories or whatever. Process automation and control is actually very closely related to this problem. In fact, when we get into multi-armed bandits in a minute, we'll see that connection even tighter. There's some very good papers published, and they're in the reference lesson notebook on optimizing ad serving and recommendations using reinforcement learning to both work around some of the limitations at scale for massive organizations, like if you're Netflix and YouTube, for example, but also doing a more sophisticated and intelligent job of serving stuff. And then, of course, finance is always this area that exploits every possible technology to try to gain an advantage. And if you think about the way I described reinforcement learning up here, a lot of these problems that I've laid out are really sort of time sequential things where I need something to work through a sequence of steps or navigates an environment or whatever in some order. And that model is generally applicable, and reinforcement learning is a good model for attacking these kind of problems. At the core of reinforcement learning, although it extends this idea in ways we'll see, is the notion of a Markov decision process. Now, I should say, you're seeing some math here. If you're a little math phobic, I hope you won't be too intimidated by this. Again, what I'm trying to do is give you sort of the gist of what's going on, what these things are trying to accomplish, and you can come back and learn the math later. This is a big area. It can be a little hard to get your head around, but if you just attack it a piece at a time, and hopefully, over time, you'll actually find that you've become expert at it. So the basic idea in a Markov decision process, as I describe it here, will be very similar to what we were saying a minute ago about reinforcement learning. There's some sort of space of states. They could be like positions on a chessboard and moves I make or whatever, what pieces have been lost. They could be some maze that I'm navigating, etc. And sometimes this current state of the system is called the context, and we'll see that word a lot in multi-armed bandits. There's a set of actions that can be taken in a particular state. There's some transition function that describes the probability that if I'm in some state at time t, some state s, and what's the probability I'll transition to a different state s prime at time t+1. And usually the next state is picked stochastically based on the probabilities of selection. It's usually not deterministic, but it can be in some cases. And then there's a reward function that determines what reward we receive at time t following that action that we just took. And this is based on a very important idea called a policy. We want to develop a policy that optimizes the way that we interact with this Markov decision process, this reinforcement learning system, whatever, to get the maximal reward. Okay. It was something I was going to mention and I just forgot what it is. But anyway, it'll come back to me. All right, so I have a little bit of math here, probability and so forth. This last equation I'll just mention now, which I mentioned this idea, we want to maximize our cumulative reward. It's in some cases, we might actually discount rewards into the future as we're considering the reward that we got now. There is this process that happens a lot, excuse me. That was loud. There is this process that happens a lot where we might want to be somewhat greedy about taking the best choice now, but we're actually going to be computing in the future. We'll come back and analyze our rewards that we've received up to that point. This is actually one of the areas where reinforcement learning breaks down into areas so-called policy-based versus, model-based versus model-free. Mostly we'll be dealing with model-free, and I'll come back to what that means in a second. But the idea here is that we're going to accumulate the rewards we're seeing, but we're going to go back and sort of reassess at each step how we're doing based on the history of rewards we received. And this gamma value is usually less than 1, and it's basically a way of discounting the future as we evaluate the present. The one thing I now remember what I was going to say, and that is to make a distinction between what Markov decision processes are and what reinforcement learning is all about. In Markov decision processes, the assumption is that the observer, this agent, actually has full view of the state, and usually can also know exactly what the probability distribution is for moving from one state to the next at time t. Both of those assumptions are relaxed in the reinforcement learning case, and typically the sort of things we need to learn by experience, by trial and error, so forth. Okay, so and just to compare those a little bit more carefully then in this section, as I said just a second ago, the transition function, the probabilities of moving from one state to the next are not known in advance in a typical reinforcement learning problem. So we just have to learn them by playing a simulator, a game, or working with a real environment and seeing what works in practice. And this often means that things have to be run repeatedly over and over again, trying different scenarios, trying to find the optimal fit and then leveraging that to achieve the best results over time. So that correspondingly means it's harder for us to determine an optimal policy of things that we should do because we don't really have a full view of the state that we're working in. So how do we make that choice? There's also an idea as defined in reinforcement learning of a reward signal. And this really encapsulates the desired goal of the system. Either I want to win the game, or if I don't win it, I lose it, or I want to accumulate as many points as I can over some time frame, or I get 1 point every time I stay alive, like this cart pull problem. Every time it doesn't fall over, I get a point, so I want to maximize the total points. That's the sort of thing that the reward signal encapsulates. And then this value function is about computing in some way what this maximal cumulative reward is and how I can optimize it. A couple of other terms you'll hear used a lot in episode. This is like one instance of playing the game. I start from whatever default behavior or random behavior or state of the game, and then I run it to completion and see how I do. And then we often talk about rollout, which is I might either in some cases, I might be using rollout to do some training, but most of the time, the way we'll use it here is that I've got a trained model or a trained policy, and now I'm going to use it to see how I do, see how well I am at keeping this pole balanced and so forth. All right, let me come back to this idea of a model. A model might be a situation like, say for cart pole, this thing is going to slide back and forth, and I'm going to try to keep the pole balanced. We'll actually explore this a little bit. I can model all of this with physics. If I ignore friction and all the things they told you about when you did your first year physics course, I can actually model the dynamics exactly. I can build a model that would predict in the future exactly what will happen at any starting point. I can, this episode I mentioned, I could predict exactly how it's going to go if I have a model that's accurate enough of the system. Another way that model is used sometimes is in training, like a neural network that is effectively an approximation to the function that would describe how this environment would play out in various scenarios. That's a model-based system, and it can be used for things like planning exactly what's going to happen in the future if I start from a given state. Model-free would be the case where I just by trial and error, I figure out what the right thing is to do, but I really don't have this sort of mental model, so to speak, of what's actually going on. I'm just learning the steps I should take, given the particular state that I find myself in. And they're often thought of as separate, but one of the things the book does really well, reinforcement learning, is show how similar they are in a lot of specific ways, and it builds kind of a universal way of thinking about both problems and sort of the play or how they play off each other when you're either model-free or model-based. All right, that was just sort of a very fast overview of the core ideas of reinforcement learning. Let's actually talk about a few examples. One of the things we work with a lot, not just RLlib, but a lot of reinforcement learning training and actual research environments are the so-called OpenAI gym environment. This is like a collection of gyms or exercise, if you will, environments that simulate various problems that you can then use for training algorithms and so forth. And one of the most famous is so-called cart pole. I think of this as like the hello world of reinforcement learning. If you're not from a programming environment, most language books, like Pascal, I've written one on Scala myself. Usually it's sort of a tradition that the first program you show prints hello world. And I think of cart pole as a good example of this. What I've done is given you a screen capture here. I think if I open this link, it'll actually show a live, look at that, it's not working, how interesting. So this should be showing the actual live event running, but we'll see it later. I'll show you a video later where you can see what it's actually doing. But you can imagine that it's sliding back and forth on what looks like a wire or something. It's only one dimension. And the idea is to properly pick the velocity of the cart, either left or right, to keep the pole balanced because of its natural tendency to fall over. So here, going back to our terms, the state is actually 4 numbers. It's the the position along this line of the cart, the velocity of the cart at this particular moment, the angle of the pole, and the angular velocity, how fast it's rotating. And those four things, again, you could model with physics exactly what you would need to do with the cart to keep the velocity, the angular velocity 0 and the pole position or angle 0. But we'll actually just learn through trial and error what's the best thing to do. The only actions in this simulation environment are either increase or decrease the cart's velocity by 1 unit, and they don't really define what the units are. So a negative velocity basically means that I'm kicking it down to go left if I happen to be moving right. The transition function is actually deterministic in this case, and it's actually determined by simulating physical laws. We could write we could do the physics to actually write a function that gives us exactly at any given state what we should do. But in the reinforcement learning context, we'll actually just learn this by trial and error. The reward function is a constant of 1 as long as the pole is upright and 0 once it falls over. So to maximize the reward means basically to balance the pole as long as possible. So one of the games you play, if I can put it that way, of computing the reward when you're trying to accomplish an objective is structure it in a way that your model or your environment does what you want to do. We'll see an example of this later. Actually, I think it's the last one we'll get to, where you actually shape the rewards to make sure that you get adequate exploration, because by default, this environment that we will have set up, it could achieve a reasonably good result just by staying in one state the whole time, taking one action the whole time, but that's not what we want. We want to see it explore the world, and so we'll see how to do that. And then the discount factor I mentioned, we won't discount any rewards. We'll just take all of them, add them all up, and then try to maximize that quantity. All right, let's actually run this. You can follow along at home either by just watching me hopefully succeed, or you can try it yourself. Now, if you've never used notebooks before, just quickly, what you'll notice is that all this text that I've been showing you is actually just markdown. And then when I do shift return, it actually evaluates the markdown. Same with this one. Now I'm in a code cell, and you can always tell if it's not obvious by this little empty bracket here. This shows I haven't evaluated this. If I do shift return here, or I could click the arrow up here, this is going to import a bunch of Panda stuff, including Gym, NumPy, Pandas, and JSON, which we'll use at one point or another. Here's an example of how we make an environment that's an example of this cart pole. You always start by resetting it. It's a bit awkward that it doesn't do this with a constructor, but this is sort of the convention. So this puts it in some initial state that's randomly chosen. And again, those four numbers are the position and velocity of the cart, the angle of the cart, and this would be in pi units or radians, and the angular velocity of the pole. Now, whenever we take a step, we're actually going to see a new state come back. We'll get the reward of 1 if we're still standing, and whether we're done or not, and then some extra info that's sort of random. So we're not done yet because we're still alive. We did get the reward of 1. If you look at the numbers, they did change just a little bit. And then rolling out is where we do this simulation. We have this policy, and or we're trying to train a policy, and we're just going to run repeatedly. And what this particular random rollout function is going to do is it's just going to randomly choose the next velocity. And remember, I mentioned that's what you pick as the action you can take. It can either be 0, which means I want to move left, or 1, which means I want to change the velocity. Let me say that to be clear. I'm not actually changing where my position, I'm changing my velocity. So 0 will mean that I take the velocity down a step. 1 means that I increase it by 1. And if I do this several times, and what it's doing, yeah, it just ran several times. If I look at the rollout, sorry, talking and not paying attention to what I'm doing here. So I defined that function. Now I just ran it twice. And the first time I ran it, I managed to stay up for 24 steps. And the second time, just 12 steps. The maximum that you can actually get is 20 steps, or a value of 20 is the reward. So what this tells me is that just making random choices is a really bad policy because it's never going to give me very good results. And we can run this again. you know, oh, that's interesting that we got the same thing there once. And none of these are actually up to 30. So that, you know, oh, wow, I actually got 99. That is completely amazing. I've never seen 99 doing this random rollout. But it just goes to show that probabilistically, you're occasionally going to get very good or very bad results. Okay, so the first exercise is, and I think we'll do this together because it's probably a little bit easier, is to actually put in a little better policy. And the way that we're going to do this, and I'll just show you the solution here in a second, is rather than choosing these policies at random, what we'll do is make some intelligent choice about what that action should be. So we'll do this by, see, what did I want to do? Oh yeah, so we have a couple of sample policies here, and what I can do then is fill in this function that I had up here in random policy to pick the right action. Now, if I just run this right now, it's going to fail because it has these assertions at the bottom that try to see that you've gotten at least reasonable results, and it's showing that we got terrible results. Now, one of the ways you can cheat is that almost all of the exercises in these lessons actually have solutions, and they are in this, it's actually here under solutions is this folder that it provides solutions. So let's just look at the way to do this. So I said we have these sample policies, and what we want to do is, you know, while we're still alive, while we haven't fallen over, we want to call this policy function to tell us what the next action is that we want to do. And then we can take a step in the environment, you know, with that action to see what new state we end up in, what reward we receive, if any. If we fall over, it'll be 0 at this point. And then, you know, whether we're done or not, whether we've fallen or not. And then we'll just, you know, sum up these rewards over time and see how they do. So what we've done here is I've actually defined, this was in the actual statement of the thing. You know, I could return 0 as the next choice, meaning, you know, take the velocity down a notch, maybe even go left. If the state that comes out, and that's again this, I get this 4 tuple, the 0th element is the position. If that is less than 0, then I'll pick 0 as my velocity, or I'll pick 1. And this just kind of does the opposite thing, the second policy. So we just run this. Oh, I forgot to do the import. I'm in a different notebook, so let's do all this stuff properly. There we go. And what it did actually is it tried the 2 policies, and you can see that the second one is actually the smarter thing to do, meaning that if the state is less than 0, or the particular position, then I probably want to push the velocity up rather than down. Otherwise, if it's greater than 0, I probably want to go the other way. An even better policy would actually, and this is where we're actually running these, by the way, an even better policy would be to look at the velocity, or rather the angular velocity, because that's kind of the most crucial thing. You know, is this thing falling to the right, or if it's falling to the left, that's probably going to determine which way I need to move the cart. So anyway, that's sort of the gist of it. Actually, let me go back to this quickly again. So, you know, very specifically, the way that we tried to determine the best policy is we came up with a couple of sample policies that we statically fixed. We tried each one in turn by first calling the policy with the current state to get the next action we should take, then taking a step in the environment with that action and seeing what state we got back, new state, that is, what reward, and whether or not we're done. We added those up, and we stopped when we were finally done, when we basically fell over. These are not great policies, but on average, they're going to be better than the random one that we used before. Okay. And the last, so these are kind of teasers I'm giving you in this first lesson. We'll come back to more depth as we go. And someone suggested I zoom up a bit. Let me do that. Okay, that's probably a little easier to read. Okay, now we'll actually use RLlib with cart pole and a very popular reinforcement learning algorithm called proximal policy optimization. There's a lot of words here that may not make a lot of sense to you if you haven't worked with this before. I have a link to the paper. I have a link to the, I think this is the link to the Ray RLlib documentation for this. What we're going to actually do is something that's a little bit closer to the way you would do a real reinforcement learning training problem. We're going to use Ray Tune, which is the Ray hyperparameter tuning framework that will help us train this thing. And what all those things mean is when we talk about hyperparameters, these are things like what should my learning rate be? What should I use as that gamma for the discount factor that I mentioned earlier? If I'm training a neural network, what architecture should I use? And what are all the sizes and of the, and are they like convolutional layers and all that kind of stuff? These are all hyperparameters that you have to decide on before you actually do the real training with the data to get the model that you want. And RayTune is built for that purpose. So RayTune and RLlib are well integrated together so that we can use Tune to train with this PPO model or this algorithm and come up with a better model. And what this is actually doing is those little rollout steps that we just did manually, it's going to do a lot of those in parallel, gather the results together and use something called stochastic gradient descent, which I'll describe in a second. And when it gets better results for the weights, it'll broadcast those updates for the policy out to all of these rollout agents. What is stochastic gradient descent all about? If you've done any machine learning before, you probably have heard about it. It's the idea that I'm going to try with a set of weights for my policy or my model, whatever it is I'm trying to train. I'm going to see what kind of results it gives me, and then I'm going to adjust those weights to get hopefully better results and do this iteratively. The gradient descent part is the idea that if my error is like modeled as a hill, and this is often the way it's done, then I want to move downhill towards the minimal error. The height being the amount of error, I want to move downhill. So I want to descend. And the way that we calculate that descent is find the gradient or the slope that maximizes, hopefully in the right direction, the descent that we want to do. And we do this stochastically because we're going to be iterating, picking a set of data points, trying to improve the model, then another set, trying to improve it again, and hopefully converging to a good model in the end. So that's what PPO is doing for us. You don't need to know a whole lot about it. Actually, this OpenAI post is pretty good about explaining the gist of it. This happens to be a very good model that people, or a very good algorithm that people use a lot. All right, so here's a gist of how you would do this with RLlib. So what we're going to do is import Ray, our amazing framework for doing distributed computing. We'll also import a few things from the RLlib and Tune libraries. That should finish quickly, I hope. There we go. Now I have this shell script that's going to run and tell me whether Ray is already running or not. It should almost always say this, that Ray is already running. The reason I have this script here is because this whole tutorial environment is designed to be something you can run on your laptops if you want, but also run in this cloud environment that we have where Ray is already running. And that's what this is showing me. If Ray isn't running, if you do this on your laptop, you'll get hopefully an informative message that shows you what to run to start Ray on your laptop, with a terminal window. And by the way, if you need to start a terminal window, especially today, the easiest thing to do is click this plus that takes you back to that launcher view, go down to terminal, and now you have a terminal view into your environment if you need it. Actually, I'm going to close that because this will get cluttered pretty quickly. All right, so once we know Ray is running, then we're going to initialize Ray in this driver program, as we call it. It's basically the Python environment. Address equals auto says, I know Ray is running on this machine, so go ahead and ask it for the information you need, like the IP address and so forth. So you should see something like this. Your IP address will be a little bit different than mine. Ignore readnet error equals true, just lets us reevaluate this cell, and it won't complain too much that we've already initialized things. And we won't log information to the driver program, which is this process, more than we want to. You could leave either of those off, really, if you wanted. If you're having trouble starting Ray, try clicking this troubleshooting link. This is actually another notebook, and hopefully it will give you some guidance about what might be wrong. you're more likely to see a few problems on Macintoshes. Like for example, and I think this isn't Mac related specifically, but if you happen to be running a VPN, that confuses RAID. So there's a way to get around that. All right. Now this also, let me be clear about what this link, what this cell is doing. If you're running on a laptop, this is the link you would click to open the RAID dashboard. As I mentioned, we gave you the link to the RAID dashboard in the cloud environment, so you should just click that link and ignore what this prints. You'll notice that it prints localhost. This is obviously not going to work on your laptop when you're doing things. Okay, and then there's a little bit of, okay, I guess we're done with the RAID initialization part. It looks like it worked. If you saw something like this, you should be good to go. If you saw errors, then you can ask in the Q&A for help, and hopefully one of us can help you. All right, let's go back to training. So we're going to configure a few things. The num workers would be, like if I had a really massive model to train and I had a lot of resources, then I might have use a very large number of workers. These roughly correspond to processes in my system. And typically they correspond one-to-one with RAID processes in particular that are going to do the work over a cluster. We'll do iterations of the stochastic gradient descent pass that I mentioned 30 times. And we'll pass in chunks of data, 128 at a time. And we're actually going to configure a neural network model that will have, this is 100, it's actually a 2-layer model that's a 100 by 100. And then the number of CPUs per worker. The reason this is set to 0 is this just works around a problem where if we set it to 1, it would actually pin each core we have available to a worker, and that's just not convenient for what we're doing because we're learning. We're going to be spawning a lot of workers, and we don't want them, especially ones that are no longer being used, to simply take up all our resources. All right, so these are parameters we set in this config environment. We're using the default config that we imported up here, right there. It's specifically for PPO. Actually, I'll show you what it looks like in another notebook if you're curious, but you could certainly put this in a cell and see what it prints. Now we'll initialize our agent. This is actually going to do the training for us. And you can see it's printed some stuff. You can use GPUs if you have them available. Okay, so now we'll actually train our environment for n steps, and we'll just set it to 10 for starters. And what we're interested in really is what does the reward mean over time? That should be increasing. We'll actually see it do very well sometimes and do very poorly, but it's the mean that we care the most about. So we're going to loop for 10 times, train this agent, and it takes a minute to run. And then we'll actually plot the results and see what we got. So while this thing has a star here, it means it's still running. You can certainly click through more cells if you want. They'll just wait until it finishes. Someone asked, how is setting num workers to 0 versus 1? I didn't see the timing on this, but as I just said, setting it to 0 just means don't pin a worker or a core to a worker. Let more than one worker occupy a core, and that's just a convenience for the way we're setting up the tutorial. In a real production scenario, you might want to just have them pinned so you don't have preemption happening. All right, this takes a little while. You can see it's finally coming up. I should probably change that number to 5 because it's a little slow in these virtual machine instances. You can see that the mean is nicely increasing as we get smarter. And we also have plenty of times where we achieve the maximum of 200 as our score. But again, it's the mean that we really care about as the thing that is indicative of how good this model is. And this will take a minute to finish. While it's finishing, let me check some comments here. Okay. So we're getting pretty good now. At this level, after 7 passes, or 8, it's actually very close to achieving a maximum that's close to the mean. Now, things start out randomly, right, when you start an episode, so you can never guarantee that you'll always be able, with the limitations of this environment, to recover from a really bad starting state, so that you can see that there's some minimum runs where we've still got just 42, even though on average it does very well, it gets close to the maximum. And that's just sort of the typical real world we live in. Let's actually plot this. Start bokeh. Here we go. So these are pretty good results, but with very wide error bars, basically indicating the minimum to max runs. But over time, the mean got better and better. So we successfully trained this policy. Also, because sometimes these graphs don't work for whatever reason, I do have, in most cases, images of previous runs, and this is very close to that. So you can see how things work. Okay, let's pre-print the results. This is a way of seeing a lot of gory detail. I actually enabled this setting already. This thing would be extremely long, but I turned on enable scrolling for outputs. So that's why it popped up this bar. But if you really wanted to go into details, you could look in here at things like this. And this is true for all the kind of models and policies that we'll train. If we look at the last one, this is the one where we were getting an average reward mean of 194, and here's the history of all the runs. So you can see they were mostly really good, occasionally a complete flop. And if we plot these, yeah, you can see that behavior here, that most of the time the runs, each episode actually was really good most of the time, but occasionally it went bad. It's kind of fun to plot some earlier ones too. Let me change this to, let's say, 2. That would be the third one. And you can see early on in the training, it was not very good. It took a while to actually get good. But let's say we go to 4. Now it's looking a little better, especially at the beginning of this training run. Maybe jump up to 7. And it's getting better and better over time. Okay, let me look at a question here. Already answered this one. Someone's asking, can you speak to how Ray makes it easier or faster to solve this sample problem compared to other frameworks? I can see it's easy to use. I'm just curious how Ray compares with other frameworks with the same problem, etc. Yeah, really good question. So what Ray emerged out of this problem, well, actually I can answer live, let's do that. Ray emerged out of this problem of researchers in reinforcement learning at Berkeley were finding that the tools they had available were not really optimal for the kinds of very diverse compute and memory access patterns that are required when you're doing reinforcement learning. And it's everything from like running those game simulators, which look more like regular applications and have very interesting patterns of how they use the CPUs, use the graphics elements, the kind of data flow through them and so forth, versus things like training a neural network versus like the ETL process of getting data in. So what they realized they needed was a very general purpose, low-level framework that gives you really maximum flexibility for how you structure small to large tasks and computation units that have state, which they use the actor model for, and then sequence dependencies between these things in a way that's hopefully reasonably intuitive for the user that's writing code at that level, while also very performant with lots of good default choices about how to schedule things over a cluster, how to scale performance, how to recover from failures, and so forth. And then on top of that, they built these libraries. RLlib, I think, was the first one that was built that leveraged Ray. So what you'll see when you look at performance numbers, and you can see these in a few of the lessons as well as in the Ray documentation, or the RLlib documentation in particular, is that it's often, RLlib is often better at various performance metrics than many of the published algorithms that were the first implementations of particular algorithms. But at the same time, it's actually a very flexible framework for building algorithms for reinforcement learning. So it supports a wide variety of the ones that exist, meaning that if you've read about a reinforcement learning algorithm and it seems to be a very good one, chances are it already exists in RLlib. And the performance is likely to be as good as or better than the custom hand-tuned implementation that was written by somebody else. So that's the value proposition of RLlib, and it gets that performance because Ray is really, really good at leveraging resources, at giving you distributed compute in a relatively intuitive way. This course, we won't, about the only thing we'll talk about Ray will be things like, starting Ray init and so forth. Everything else is high level in RLlib. But if you needed to drop down to that level, then you'd have a lot of flexibility in how you do it. And I suggest you look at the Ray crash course for that. Another question here, what's the difference between Dask and Ray? Excuse me. That's a really common question. And the way I answer it is this. Dask is very, very good at distributed data frame kind of models, like pandas, doing distributed pandas, or NumPy. There is some work being done to add this kind of capability or in terms of libraries on top of Ray. And we think that ultimately Ray would provide better performance. But the maturity level for Dask right now is definitely there. So if you're really mostly working with like distributed or pandas and you want it to be distributed, or mostly working with NumPy arrays, then Dask is a really good choice. If you want general purpose distributed computation in Python in particular and other languages in the future, then I strongly think that Ray is a better choice for that more general purpose case. Okay, I'm going to skip the second exercise because we're already close to 11 o'clock. But basically what it does is look at using like tweaking the size of the neural network, because it's actually overkill, the one that we built. It could be smaller. So you get to play with that. And then this last point we'll come back to in another exercise where you can actually save a checkpoint of the work you've done and then come back and either just use it for serving or use it to continue training. And one of the, I think it's, actually it's one of the reinforcement learning lessons we'll get to goes into that. So what I'll do instead is skip on to the next lesson. There's a link here, it's number 2, Introduction to Reinforcement Learning. If you're in the RLlib on the left, this folder, it's this one, Introduction to RLlib. So what I'm going to talk about now is just step back for a second, talk a little bit, actually kind of continue on a couple of answers I've given already about what RLlib is all about. I said why it was created. It was trying to address a problem that people had of, I just want really smart choices made by default and an easy to use API, but I need to build this very general purpose compute environment for research and production serving of reinforcement learning. So it's structured mostly like this. It works with a lot of third-party tools. We're showing here the gym environment. We just talked about that with Cartpole. Multi-agent hierarchical. These are different ways of structuring agents, like having more than one in an environment. And you can do things like use it as a serving environment for policy that's already been trained. There's even cool techniques emerging for training with historical data. Maybe I can't simulate my chemical factory, but I have really good telemetry from its past performance. Maybe I can build a model that way. There's a lot of built-in algorithms and even some custom ones, and we'll actually use a few of the custom algorithms in a minute when we get to multi-arm bandits. And then on top of that is lots of flexible abstractions for composing algorithms in different ways, reflecting the different approaches people have taken. And as I said, this is all running on top of Ray to give you the performance and flexibility. Someone asked, is this being recorded? Yes, it is. I will post the video probably by the end of the week. There'll be a blog post on Anyscale.com with the video link that'll be on our YouTube channel, and also a reminder of where the GitHub repo is. So let me run this thing again. We already know Ray's running, but I'll just do it again. And here's the gist of how you would more typically use RLlib from the command line. You would first install it, and one way to do it is pip install Ray RLlib. You would also need to install PyTorch or TensorFlow, depending on which one you want to use. And then if you wanted to train Cartpole like we've been doing, you could train it from the command line. Windows is just now becoming available, but certainly for Unix kind of command lines. RLlib train, you want to do PPO, that's that proximal policy optimization algorithm. The environment you want to use, it recognizes all the gym environments. So if you're going to use like, what's another one? Like the walker that we're going to see in a minute, then you could do that. Further criteria about when to stop, connect to the existing cluster, and then how often to checkpoint stuff. We'll actually run this in just a second. There's also help. You can find out about how to do training as well as rollout. And you can do a lot of this much the same way we've already seen using the code just in Python. All right, so let's actually run this. You can actually run shell commands in a notebook by putting this bang in front of them. This doesn't work for every shell command. You'll see examples later where you can't really do this, but it'll work now for us. Now, I already right-clicked this menu option to enable scrolling of outputs. And if you scroll through here, it's printing out various log data. This will get longer in a second. Actually, while we're waiting for this, why don't you, we're going to use TensorBoard to view this. If you were on a laptop, you would run this command in a separate terminal window. You can't do it in the way we just ran this command. But I gave you the link to TensorBoard. Let me refresh this. This should start. Ooh, that's not good. Okay. All right, I know what's wrong. I'll have to fix that. I'll fix that in the break we're about to take. For some reason, refreshing the window didn't work. I don't know why. Maybe you should not try that at home. But if you're watching, it should eventually detect that there's actually data that's being written. And it's written in your home directory under this array results folder, what you can see here, in a default subfolder. And it's actually writing all the information, the metadata about this training process, and showing you what the success for each of these runs. And this will finish shortly. In fact, let me just go find, actually I closed the window already. Let me find my TensorFlow link, sorry. That's all the way down here, I think. I'm scrolling through another window that you can't see that's absolutely enormous. Here it goes. Here's what I want. Okay, this is good. Let me drag this over here now. All right, so if you open that TensorFlow link, this is the one that messed up. Let me close that. You can see the results as it did these different trainings of you know, the reward max. Once again, the reward mean is what we really care about. And you can also decide, you can tell it over here what you don't want to see. So for example, the one that we're looking at now is, the one we care about that I'm doing right now is the one that's default /PPO. You can also see by the timestamp that this is the more recent one and it's a universal time. So this is what's interesting. We're getting close to the maximum, just as we saw previously when we were running inside the Jupyter Notebook instead. This is now done. Now, here's the thing. There's a command down here, and I've encapsulated in this rollout script where you could actually see this thing run through different episodes. But unfortunately, that doesn't work in a cloud environment because it wants to open a window. So what I've done is I've captured one of those images as a MP4 file, and then there's this way of playing it in Python. So I'll just play one of these episodes for you so you can see what it looks like. And you can see that it's gotten reasonably good now at you know, knowing where to move the cart to keep the pole balanced for some number of seconds there. And that information was actually taken from here. This is like the last checkpoint. And if we reran the rollout script, and I really ought to show, this is a change I'll make. Well, here it is right here, actually. This little script is actually what's being run by this shell script here. It's going to do RLlib rollout, this checkpoint path. So what the script does is figure out where this path is at the checkpoint after 20 steps for whatever timestamp we're looking at. And then it runs PPO. And what it would do is run about 20 of these video pop-ups, one for each episode. And I just showed you one of them from a previous run I did. So again, unfortunately, I can't really show you this inline. I think I know how to modify the RLlib command to support that. But for the time being, if you're not running on a laptop, you can just look at this video to get a sense of what you would see if we were actually running the rollout command. All right, let me finish with a few more concepts, and then we'll take a break and start with policy optimization, or sorry, multi-armed bandits. I'm kind of reading and talking at the same time. Just a few other details. I did mention that RLlib is already integrated with the gym environment for things like cartpole. It has some other environments built in too, so you could have multiple agents interacting with a single policy, a multi-agent scenario where they're training different policies and interacting in some way. There's different ways that you can define how loss or reward are measured, how you configure batches for processing data. And then there's a whole bunch of ways that things can be configured together in RLlib for defining things like the policy, the optimizer for policy. You can define your own training classes, all of which have these typical methods where you want to train, you want to save a checkpoint, you want to restore from checkpoint, and you want to compute the next action. And RLlib supports distributed training too, where you might have a whole bunch of these workers that are doing this kind of rollout to do either training or replay in the background. And then there's a trainer that's coordinating updates globally. So we saw that PPO does this. It trains a bunch of stuff in parallel, and then it has this gradient descent process that finds the best results among all of those inputs, and then sends those results back to the rollout agents. So let me just scroll down to the bottom here. There's a lot of stuff here you can read on your own. The last thing I want to mention is I have a list here of all of the current algorithms that are supported. I mentioned what we'll be using, and I've already used proximal policy optimization. We'll also use a little bit of DQN, deep Q networks, which was the first algorithm that combined neural networks with a classic algorithm called Q learning. I'm not sure we'll get to this, but anyway, you can read more about each of these by clicking these links. They also have links to the original papers. And a lesson that I'm working on but didn't finish in time will try to make sense of this landscape in a way that helps you sort of navigate what should be most interesting to you. Okay. And finally, I did mention this reference notebook. This has links to books, blog posts that are really good, other tutorials and courses, and then a lot of the papers that you might find useful if you're into that sort of thing. All right. It's a little after 11, so this is what I'm going to do. We'll go to multi-armed bandits next. We'll take let's take a 5-minute bio break, if that's all right. And I'm going to type answers to some questions that have been posted while we're taking that break. So go ahead and take 5 minutes, well, actually 6 minutes. I have 4 minutes after, so let's come back at 10 after 11 and we'll pick up where we left off. All right, welcome back. Somebody asked about getting the best checkpoint, and one of my colleagues, actually the person who wrote Tune, said you could get it this way. For example, you could do tune.run at for the final checkpoint, and then ask the object that comes back to give you the best checkpoint. Some of the other questions I answered in line, and let me just quickly scroll through what my colleagues said about some of the other questions to make sure that I didn't miss anything important. I think I covered most of these. One section of the documentation, there was a question about like scaling and using Kubernetes and so forth. One of the new systems we've built is called Serve. And if you look for that in the docs on the Ray site, you can see some information about how we're trying to enable a scalability of HTTP endpoints for things like model serving and so forth. I think that's probably it for now. Okay. I'll come back to, there's a couple other questions I'm getting answers to, and I'll come back to those when the answers are available. All right, let's talk about multi-armed bandits. This is a problem that actually predates sort of what we think of as machine learning today, and it's very much driven by the problem of like optimizing control in an environment. leveraging the sort of Markov decision processes that we mentioned too. The idea with, let me just click into the introduction. This is number one. The main idea here is that this problem domain is inspired by the gambling machines, the slot machines, where you pull an arm and hopefully eventually get a reward. Most of the time you don't, which is how the bank always, or the casino always wins in the end. But the idea is, what if we generalize this to have multiple arms where we don't know what the reward is or the probability of getting a reward? We just have to try these different arms and try to discover which one will give us the best reward. In the simplest case, we'll assume that these probabilities are static, that all we need to do is keep trying and learn them that way. There's also the notion of a contextual bandit, where each time I pull the lever, it might actually change some state. And it may even indicate that state to me by changing the graphic that's shown or something. I don't know if casinos would give you that much information or not. But the point, the complication being that not only might you have multiple arms to sort out, but the actual state of the environment and the reward you get could actually change from one run to the other. So how do you sort of find the optimal point there? The two ways in which multi-arm bandits simplify the general reinforcement learning problem are described right here. Oops, I didn't really actually mean to click into that. One is that bandits, is the simple term, they don't attempt to learn the best actions to take from more than one state, whether it's a state that's slowly evolving, which is sort of intermediate with the whole context idea, or whether it's completely static or whatever. The state, in the simplest case, the probabilities are never going to change. I can pull the arm as many times as I want. I'll always get a consistent result. It might be a probabilistic result. You know, there might be some Gaussian behind the scenes that determines, you know, what answer I get, but it'll never change otherwise. It's fixed. The other thing that's different between bandits and the general problem is that the action only affects the reward that you receive. You know, I decide which arm to pull. It's only going to affect the reward. It does not change the state itself. Whereas in the general case, you know, when I'm interacting with a game like Go or Breakout or one of those games, every decision I make, every action I take affects the game state. You know, I put a new piece on the board or whatever. That's not the case in bandits. So bandits are a slightly simplified problem. They are not trivial. They are used for real problems in the real world, besides winning in a casino. But they also give us a good vehicle to look more closely at some of the concepts of reinforcement learning. So the contextual bandit, again, is the thing where the state may actually change between pulls, but my pull doesn't affect what state I see. This could be a completely random process or some algorithm that picks the next state independent of the action I take. And then two things that you'll also, we've talked a little bit about one of them, but one of them is whether you measure reward versus regret. In this case, regret is defined as the difference between what would be the best possible reward I could get if I had a perfectly trained system versus what I actually got. And sometimes it's actually useful to measure regret rather than reward, because some algorithms can actually put bounds on the regret more easily than they can the reward. We'll also explore this exploitation versus exploration trade-off a little bit more detail. The gist I want you to get out of that part is the kind of concerns that you should think about when you're trying to decide how to trade those off. You'll see what I mean in a second. Okay, I won't recap the summary. It's kind of the same as what we saw. I will mention a few of these real-world applications. If you're concerned that this sounds like it's a trivial problem, check out this paper. It's actually, I think it was written by some folks at IBM, and it lists a whole bunch of really interesting uses for bandits as a way of solving some real-world problems. Okay, with that in mind, let's go to this second lesson, exploration versus exploitation strategies. Now this one is maybe the most mathematical of any of them, but I don't really want to get bogged down in the math. Again, I just want to give you a sense of the kind of problems that you need to think about and then talk about a few examples of how this is addressed. So what would make a good algorithm for this problem? Well, one is that you really do want it to explore all the possible states or actions to find the optimal reward. And it should be reasonably aggressive about doing this. You don't want it to go a long ways on a suboptimal path before it actually discovers the optimal choices. When it actually decides to explore, you really don't want it to just randomly pick something new. Ideally, you'd like it to pick something that in some way you think will be an optimal choice, will be a good thing to explore. You would hope that the algorithm would converge fairly quickly to the optimal reward. Now, I'm talking really about the simplified bandit model where state doesn't change. If you're in a contextual bandit or an evolving scenario, then this has to be relaxed. You'll never stop needing to explore because what is optimal now may not be optimal forever. And the last one is, especially in the static case, you'd really like to stop exploration completely if you've truly found the maximal action to take. But if it is a case where you can't stop, you'd like to minimize in some intelligent way how often you explore. So let's talk about a few algorithms and how they address this. One of the simplest ways to do this, to balance this exploration versus exploitation, is called Epsilon Greedy, where epsilon is usually some small number. And the idea is in Epsilon Greedy that most of the time you're going to take the best choice that you know about already. But then for some small epsilon percentage of times, you're going to take an exploration choice, but randomly pick which one you choose. Now, here's how that stacks up with the qualities that we just described. If you pick a very large value for epsilon, like let's say every 10th step I'm going to explore, then you'll very quickly converge, or you'll very quickly explore the whole space of actions that you can possibly choose. The disadvantage of this, one of them, number two, is that it randomly picks the next choice, and that may not be the right thing to do. There's no intelligence applied at all in this simple algorithm. Number three, it does converge to the best choices fairly quickly if you have a high value for epsilon, but there's a big penalty for high value for epsilon, and that's number four, which is it never stops exploring at that percentage, even if you've actually found the optimal choice. So if you happen to say, let's say you have a 10-armed bandit and number 5 happens to be the best choice, and it's a static bandit, let's say, where it's never going to not be the right choice, then you would like it to 100% choose number 5, but it will still choose the others, for whatever the size of epsilon is. So you'll actually get a lower cumulative reward with a larger epsilon, because you'll spend more time exploring stuff that's suboptimal. Whereas a smaller epsilon will take longer to get to that optimal choice than a larger epsilon, because it won't explore it as aggressively. Two of the ones that we'll actually use in examples are upper confidence bound and Thompson sampling. They have some fundamental differences from the statistical point of view, in the sense of UCB, upper confidence bound, is a so-called frequentist approach, where I'm just going to measure things and then just kind of make my choices based on measurements. Whereas Thompson sampling is more of a Bayesian model. It tries to build up a belief network about what the right choice is and then make that choice. Experimentally, Thompson sampling does tend to work better, but UCB has better theoretical properties, and it has been analyzed more thoroughly. Now, there's this sort of complicated looking equation here. Let me just give you the sense of it, and then we're actually going to move on to the next lesson. The idea here is when I'm trying to pick the maximal optimal action for the next step, this Q value is the sort of placeholder function for something that tells me, based on my current knowledge, this is the best choice. This is the one that gives me the best reward. Excuse me. So if I never wanted to explore, this equation would just have this value, and actually the constant C would be 0. Excuse me. Okay. Now, what is this square root thing all about? This is the one that says, all right, as time increases, I'm going to weight whether I explore by the log of time. What does that do? Well, if you look at the logarithm of something, it rises rapidly and then it starts to taper off at greater time. So it's basically sort of building in the assumption that I'll probably have gotten close to the optimal choice at some large time scale. So I really don't want to explore as much as I get higher in time. So it has a nice factor of adjusting how much we explore. The counterfactor, if you will, this n sub t of a says that it's really just how many times have I actually looked at A already? And if I've looked at it a lot, then there's probably less reason to explore it again. Now you might say, well, what if A is really good? Well, that I've actually accounted for in the Q function. So what this correction factor says, this is my exploration term, is based on how aggressive I want to be, I'll set my constant C. But over time, I'll explore less and less because log time decreases, log of t, the slope of it. But I'll also penalize the actions that I've already visited a lot on the assumption that there's no reason to explore them if I've already been there a lot. So this is a good example of an algorithm that can relatively quickly find the optimal answer depending on the value of C. C is a hyperparameter again. I don't really know how to pick it except by trial and error. It does do a pretty good job of picking the optimal case most of the time, but also has this correction factor that has me do exploration. It's a pretty efficient algorithm, so I usually do converge to the right answer relatively quickly. But the way the thing is constructed is that I avoid a lot of unproductive exploration. By the way, that the log t and the 1 over nt work, they actually keep me only exploring what are most likely to be useful cases, but do less exploration over time. So this is an example of a more sophisticated approach than Epsilon Greedy. It has a lot of nice properties, and it turns out that most of the time when you do multi-arm bandits, you'll use either upper confidence bound or Thompson sampling. And as we'll see, there are versions of both of those built into RLlib, where this Q function is actually just a linear function, where I'll assume that the reward and the action taken have a linear relationship, X, AX plus BY equals C kind of thing, or equals Z, I guess, better, as opposed to something more complicated like exponential, logarithmic, whatever. All right. Hopefully that made a little bit of sense, that we want to have a good algorithm that knows how to balance exploration versus exploitation, and that will give us, over time, the best cumulative reward. So let's actually look at a couple of examples. And we'll start with this notebook 3 to do that. So this will be a simple bandit example. Let me just start evaluating cells here. So we've done our imports. We're actually going to construct our own environment. We looked at the cart pole built-in environment in GEM. There's a base class in GEM called gem.env, and we'll just create our own, our simple contextual bandit. And what we have to define here, and this is sort of the typical kind of stuff you do when you're creating these things, is we need to define what are the possible actions that I can have. And in this case, we'll have 3 arms. No particular reason it's 3, just kind of a random choice. The observation space is what can we observe, and it's basically going to be a random XY set of coordinates between -1 and 1. This is the observation that would come back to us. And then the current context will be, this is a contextual bandit, so we can do, after every single step, we can change the context. In fact, the way this is written now, we're not even going to do that. We're going to fix it when we initialize this bandit. That's in this reset. So here's where we set it randomly, either some number between -1 and 1 will be our context. Sorry, it's actually -1 or 1. We pick one or the other. This actually shouldn't really be floating point. And then here's the rewards that are defined for each arm, arm 1, 2, and 3, for each of those contexts, either -1 or +1. Now, if you stare at this carefully, remember what I just said about a linear upper confidence bound, linear Thompson sampling? There's actually a linear relationship for arm 1, for arm 2, and for arm 3. There's a linear relationship between those reward values and the actual context value itself. And if you think about it, if the reward is 0 here, then you never want to pick the second arm. So ideally, we would only pick, if the context is 1, we would pick the first arm. If the context is -1, we would only pick the second arm, sorry, the third arm. Index is 2, in fact, in this array. So you can eyeball what the right choice is in this particular sample bandit. But what we want to do is see if our algorithm can tell us what it is. So as I said, we saw this earlier, we call reset to start things for each episode. And then we step by passing in an action that we want to take. We find the rewards for that particular action from this structure here. And then we return the results. This is going to be the new state, which is going to be some value in the observation state. We'll sample that. The reward value we got, which is going to be one of these numbers, whatever, in here. We return true. We could stop at any point. And then there's as this sort of extra open-ended structure for the info object, we're going to return the regret, which will calculate sort of arbitrarily as 10 minus the reward. And then I have this function to actually print it out, this object, if you want. So let's evaluate that. So we've defined that. Let's create an instance of it. I've reset it to some arbitrary value. And then if I run it 10 times, notice that the current context is going to stay -1. The observations are fixed. But if we go back to this thing up here, if the context is -1, my best choice is always this last arm. And sure enough, if I pull that arm, which is index 2, I get a reward of 10, and I get the minimal regret of 0. So I want to minimize my regret, maximize my reward, and that's the case here. If I change this, let's see, I think I have to do this one too. Okay, so this one is now +1. In this case, I wanted to pick the first arm. That's this one, index 0. I get a reward of 10 and a regret of 0. So that's our little bandit context. That's the one we're going to use. And now let's actually apply this with linear UCB. So we'll make sure that array's running. This should, of course, return that it is. Yes. We'll initialize array like we did before. Once again, this is sort of the kind of thing that you would do with any sort of exercise or training environment. We're going to define some stopping criteria. We'll either stop at 200 iterations or a total timestamp of 100,000, I think it's milliseconds, or if we reach a mean reward of 10. And in fact, that's the one, this is going to be very easy to train. We'll hit that very fast. Whereas one of the exercises that I'll show you, when you do a nonlinear relationship between the context and the reward, it just goes forever because it can never find a good result. All right, and also the config, we have to tell it what environment we're using. We'll import, now this is actually not needed. I did this kind of for myself to learn how does it actually report progress inside a Jupyter notebook? And it turns out this is the default behavior when it detects it's running inside Jupyter. It uses this object to print out the results. All right, and you can see it's running. We're using tune again to run this thing. If you pass a string like this, it knows that we want to use this algorithm, linear upper confidence bound, to do the training. We passed in the config we defined, the stop criteria. This was not necessary, as I mentioned. I put in verbose output. You can reduce that if you want. And I specifically don't want it to reinitialize array because it's already running. So you could use any of these arguments that you care about. And as you can see, it did a whole bunch of training runs, printed out a bunch of stuff. And if we look at how long this took, well, actually, this is not going to be very accurate because I was talking. It actually finished in a few seconds. And it successfully got to the maximum reward of 10, very easily got to that level. And we could look at, actually, we look at this in TensorBoard. This linear UCB is what we just did. So let's turn off everything else. And you can see this is kind of boring because it was very easily able to train this linear relationship. So it actually didn't do much interesting. So what this one does, these two exercises, and mostly I'll let you do these on your own time if you want. I mostly want to focus on the second one. If you actually do change the context on every step, remember I said it's fixed once, but doesn't change. It actually doesn't impact its ability to train. It still trains very quickly. So that's kind of a boring exercise, but it just kind of proves a point. This one though, if I change these numbers to this, then I've actually made it nonlinear, the relationship between the context and the reward, so that it gets very confused. The last one is actually using linear Thompson sampling. I'll skip that one because we'll come back to that in a second. But let's go into the solutions for the multi-armed bandits. And I'll run that second one because it's kind of cool. I need to import some stuff here. I didn't really need to run that. Let's go down to, I think I need this. I'll skip the rest. So let's try this with the nonlinear rewards versus context. We'll create our bandit. I'm just printing out some stuff just for grins. Here's if you step 10 times, here's the results you get. And pretty much what it confirms is that you usually want to pick the second one in this case for either of those cases. So that was index 1 in the array with the context of 1, and it happens to be the same for -1. This is your best choice. So now let's try to run this. We can use the stop from above that I just defined, and we'll run it. And this time it's actually going to take all 20,000 steps. And what you'll end up with, if you look at, we'll flip over to TensorBoard in a second, you'll see that it really struggles. This is the reward mean as it tries to do this linear fit on something that's highly nonlinear. Let me just go ahead and evaluate through this and then flip over to here. Let me turn the old one off. Unfortunately, I think I may have just messed up the scale. But let's see what this turns into. That's one of the things I've noticed about TensorBoard sometimes is that it's really hard to reset the scales of these things, if they've been set by something else, but we'll see what this does. What you should end up with, though, in the end is something that looks like this for the mean reward per episode. And you can remember I said the mean reward is supposed to be 10. Well, it actually turns out to be typically averaging around 5 or 6. Here it is. This did actually finish. So we averaged about 5.5 for the mean. It never really did any better than that. Let's see what this looks like. I think this got scrolled off unless I clicked the wrong one. Oh yeah, I am looking at the right one. I think it might, the scale is probably too small actually. Try this. There we go. Okay, I clicked this resizer. So you can see what it did. It really struggled to achieve a good result, even after training for 20,000 steps. All right. Now if we go back, so we just did the simple multi-arm bandit. And let's look in a little bit more detail at linear upper confidence bound. I'm just going to talk a little bit about these right now, because for time's sake, I'd like to get back to the reinforcement learning stuff. You know what, actually, I'm gonna skip this altogether for time and go to this one example of several that we're working on that try to show a more realistic real world application. So let's just skip to this one. This is number 6. And what it's gonna do, it's really a simplified model of how could you optimize the way you trade in various markets. So we're gonna have the option of investing in the S&P 500 like an index fund, treasury bills, treasury bonds. I forget the bills are the short-term government bonds, the bonds are the long-term bonds, and then corporate bonds, this particular Moody's bond set. So let's walk through this and I'll show you some interesting data about this. It actually goes back to 1928, I think, if I remember. The data is in this file market.tsv, which you can see right here. So it goes back to 1928, 1929 through 39 were not terribly great years for the markets, as you might remember, or at least have heard. And if we do some bogus statistics over this, we get all kinds of crazy results. But anyway, DF describe is sometimes useful. Let's actually analyze this data a little better. So what I want to do is, this calculation is going to figure out if I made the worst possible investment every year, meaning that I took all of my money once a year and put it in one of these options, or I put it, or I made the best choice each year. You know, what's the kind of range of return I could get over time? And it turns out I could either lose about 5.6%, which actually isn't so bad if I'm doing something really bad, like always picking the worst option. But at best, I could get a return over this time period of 15% annualized. All right. Now, if we plot this a little bit, what I'm going to show you here is the maximum and minimum results per year. So there's some years like this one where it really would have been good to pick one over the other because the spread was huge, whereas other years just sucked. This is in the early 40s or mid 40s, late 40s. And it didn't matter which one I picked, I was going to have not a very good year. So that's all I'm doing. I'm taking that max and min and plotting the area between them. And so you can see what the possible spread is year over year. So let's define our environment then. We're going to create another bandit like we just did, where we'll have, this data is indexed by inflation. So we'll keep track of things like the inflation, the tickers, which are those 4 different options for investing. We have our data file. And then just print out some stuff when it loads. The action space is 4 because I have 4 investment options. The observation space is some box. It's actually a range between the minimum and the maximum inflation values. And it's the shape of 1, meaning it's one-dimensional. I can load the market data, and then I'm ready to roll. So when I call reset, this is going to set the year back to the very first year, which is 1928. It's going to pick a context that, I forget what this thing is doing actually. Let's see. Oh, it's going to, I think it picks the current context is one of these inflation values that are in the table, actually for the current year. And then whenever we step, we're either going to be done, and we hit done when we've actually hit the end of the data set, or we're going to determine what year we're in. So we'll march through this year over year. We'll get the ticker values, calculate the maximum reward, and then try to actually invest in that. And we do things like, so I guess the context actually is the inflation value for that particular year. So that's going to be changing year over year as the inflation number change. And we'll also finally return the regret and the year so that we can watch that data. So the usual thing, the context, which is the current inflation value for the year, the reward, assuming we picked the right, well, whatever we picked, whether or not we've hit the end of the data, and then this data about the regret and the year. And then we also set the seed to be something random just to make it work a little better. So let's actually see this in action. If we take a few steps, over some period of years, we can see that we get various results in terms of the reward, the inflation index, and so forth. So let's actually train this thing. So I'm going to train it over, I changed this to 10,000. 50,000 gives you slightly better results, but because these virtual instances aren't the most performant, I just decided to pick that. And just by this very naive way of training things, we managed to get a reward of, oh, wait a second, actually I forgot. We're actually sampling, what we're actually doing right now is we're just naively picking at random one of these things. This is a little bit better at 3.6 than the worst case that we showed, which was like -5, but it's way below the best case, which is like +15. So we get roughly like 3.5 is our, just by randomly picking an investment each year. And that's what this sample is doing. This is the best we can do. So that's not so great. I think we just did this one. We could plot this line. And guess what? If we make a random choice, we never get any better. The rewards just go way up and down year over year. but it averages out to about 3, so which is roughly right here. So not so good. We'd like this line to make a lot more sense, and that's what we're going to do now by training this with RLlib. So I'll do some more imports from RLlib. We're going to do linear Thompson sampling. That's what this is. We'll import the default config object. I think I show this, maybe not here, but in one of the other lessons, we actually can look at what's inside these things. Actually, we could do that very easily after I've evaluated this, which I guess I just did. If you're insanely curious, we could just print this out. I could type. And that's all the stuff that you can set. Notice that there's a big set of parameters for the neural network here. And because that's so big, let me just enable scrolling for it. All right, there it is. All right, let's start Ray. Let's add the extra configuration we need. We need to tell it what environment. It's our market Bandit. This is a way, notice what I'm doing here. This is the idiom that RLlib provides for taking a base config and in a programmatic way adding extra config stuff that you need. So in fact, we want to know, we need to add stuff like this, the tickers that are available, the max inflation value, which is kind of our bounds for the context, because remember we said the context each year was going to be that inflation number, and then our data file. So we can have something up here that's very generic, and then we just pass in through a config object what values it should have for those things. So it makes it really easy to train with different config settings without having to recompile static code. This is especially important to use this idiom when you're working with something like Tune, which is, you're going to hand off stuff to Tune, and then you have to have a way of getting information into it that you don't have if you were doing things by hand programmatically. So that's what this config object is doing for us. With base config, starting from this guy, add these extra values. We'll only train for 100 iterations just to keep it relatively fast. We'll train our own custom trainer object. This is a way of starting with a built-in trainer and adding some extra information to it, which is how, well, we're giving it a name, but most crucially giving it this config object. So this is another pattern. And now we're going to ask Tune to do all the heavy lifting to find, what we hope will be a really good policy and an underlying neural network. Okay, I saw this the other day. I really don't know why this happened. Oh, that's disappointing. Okay, I'm not sure why this is happening. And then, in fact, it worked for me just the other day. So there's some bug in here I need to find. So I don't think this is going to succeed. No, it actually failed out. But remember, I just said a minute ago that I put in images. So this is what it should look like right now. I mean, if it worked for you, if you didn't see those error messages, go ahead and click through these 3 cells and see what you see. But what you should see is something like this, where it has pretty big error bars and pretty low reward at the beginning, but it does actually converge to a reasonable solution. And in fact, this one I did at 10,000 steps, and you can see that by the time of like 5,000 or 4,000 even, it's gotten about as good as it's going to get. Let me close that. And if we look at the rewards for each step, actually, this is a cumulative regret. So we never get a perfect result. We're always going to accumulate errors. And in part, it's because if you recall that graph I showed you of like the min and max possible each year, it was very chaotic looking. So it's really impossible to train this thing to have 0 regret. So it's going to accumulate over time. But we have a pretty narrow set of error bars, so it does about as well as it can do. Somebody asked a question here. I see. Okay, yeah, this is a comment from one of my colleagues. That error is actually fixed in the master branch for the repo, so I'm not sure why I had, anyway, I'm not sure why it's still failing here. I thought I had the latest code, but apologies if you saw that fail. All right, so if we'd actually succeeded, we would get a good number for the reward. I think the number actually comes out, as I say in the comment here, between about 6 and 8%. That's still far below the 15%, but it's a pretty naive model. We're not really giving it much to work with. So to get 6 or 8% is at least, much better than the 3.75 or whatever percent that you get for just making random investments. All right. There is one exercise you might try on your own time, and that is to use linear UCB instead of linear Thompson sampling. And in fact, what I found when I did this was it took longer to get the answer, but it was, I think it was actually even worse than, if I remember the results correctly. So it actually got better results with Thompson sampling, and it definitely took longer using UCB. Quickly, what if we wanted to restore from a checkpoint or actually save a checkpoint? Well, one of the ways you could do this once you've done training is the analysis object, let me go back to that, is up here. Yeah, it's the result that RLlib returns with a lot of metadata about the whole training process. And from that, you can actually get information about each trial. And you can actually, like, for example, if you take the very first trial, you can get the checkpoint from it. I don't think this will have anything in it because the exercise didn't work. But you can actually look at the path to where the checkpoint is stored, and then you could actually load from that path using this. So you could create a new trainer. Realistically, this would be like your serving environment versus your training environment. Or you start from a checkpoint and you want to keep training, then you would start here. And then you could go through the whole process of tweaking the model and so forth. All right, we're nearly out of time. So what I want to do last, just for fun, is I'll go to the Explore RLlib, which is kind of where we would go anyway at this point. And this one just dives into some of these environments in more detail and lets you play with some of these algorithms in more detail. But let's look at number 2, which is the bipedal walker. This is kind of a fun example that you may have seen before. It's this robot that has to learn how to walk on 2 legs. And let's see if one of these will actually show. Yeah, here you can see it working, or just, this is actually a really crappy early training run. It's not very good, but you can see that it's starting to get smarter about what to do with its legs. And at some point, it's actually, I think if we let this run long enough, it'll actually learn to walk. But let's actually do it ourselves. All right, so we'll use this policy proximal optimization again. We need a bunch of stuff, so we'll import that. There's some utility libraries for like plotting that I'll import that are in this directory that I won't show you now. And what I did is, this is one of those things that it takes a little while to train it to get to be smart. So I actually pre-trained this thing, I think it was 100 times. And then I have this checkpoint directory right here. Let's see what's in it. There's actually some metadata and then the actual checkpoint file with the current model. And it's actually 50 steps I did. So let's set that. And we'll also grab where the RLlib results are written. So this is just a hack to ask the operating system for the home directory and to give us that information. We already know RLib's running, so I won't run this one again, but I'll go ahead and initialize RLlib. We already know where the dashboard is. And now let's train a bipedal walker with the existing checkpoint we already have, so we'll make it smarter than it was. We're going to use version 3 of this thing in OpenAI Gym. We'll go for 50 more steps. This will take a little while, but we'll just take it to the end. We'll just make a copy of the default config that goes with, this is another way to handle this. We'll make a copy of this default config and then add stuff to it. We'll make sure we're using all the cores in our machine. I think there's 4 in these default instances. Actually, we could tell here. Yeah, I believe there's at least 4 if you look at the RLlib dashboard. Although there's not necessarily a one-to-one correspondence between the number of these RLlib workers that are running and the number of cores you have available. Although this one happens to say that I have 4 virtual cores available. Let me close this thing. All right. We're going to do a stochastic gradient descent again with a neural network with mini batching of 250 at a time. These are numbers that I just sort of experimented with myself to come up with. I would suggest you play with them and see which what kind of configuration gives you better results. And here's that setting again where we don't want to just block a core with a worker. Here's another example of a default config. Actually, I think this is one we saw earlier. You can see there's a whole bunch of config settings for the neural network. We can just use the default trainer object. Let's see, name config is not defined. Is that right? Oh, I didn't evaluate this. Okay, there we go. All right, that looks better. Now we'll restore from this checkpoint file, this checkpoint 50, to the agent, and that'll kind of get it off to a good start. And then we're going to run it now for 50 trials. And we'll plot it when it's done. I'll just go ahead and key these up. And what we'll see actually is the quality of our results after 100 training runs. And this will take a little while. This will probably finish us out today. Let me check something while I'm, okay. Yeah, I think maybe 50 was a little too many for these small virtual machines, but while we're waiting for this to run, are there any further questions? This will be the last thing we do today. We're nearly out of time. Yeah, just by comparison, I have a recent vintage 13-inch MacBook Pro laptop, and this, I think this 50 steps takes about 2 or 3 minutes to run, if I remember correctly, when I did it earlier. So I should probably change this and iter to like 10 and give you like maybe a better checkpoint that's gone on. Yeah, see, I had a comment here and then I kind of ignored it, so 20 would probably be better today. But while that's running, I actually have the previous results here. So, or from when I ran it earlier. So this is what you see as behavior. The minimum reward is pretty bad until it gets up to about 30. And slowly the mean is increasing, or the median, I should say. And the min and max are both increasing as well, so that we're getting decent results. We can also do the rollout, as I mentioned previously. This is the shell command you would run to visualize this thing, and it's a nice little movie. This will not work in the cloud environment, but once that's done running, I'll show you an embedded video I have. And in fact, I may even go ahead and do that because this is going to take too long. So let me just stop the kernel so it stops training, and I can run this cell and show you what the movie looks like after it's run 100 times, or trained 100 times. So as you can see, it's not walking in any normal way that we would like it to walk, but it does actually work. It moves forward. It's not falling over. It's just not walking in a very bipedal way that we would expect. But that's, it's kind of impressive. It used a neural network to learn this. This was 100 training iterations. You should see something similar. And, once again, these environments are going to be available for another few hours, probably till like 3 o'clock, if you want to play with this some more and see how far you can take this thing. There are some, I mentioned this is homework because I don't provide solutions, but you could check out some of the other so-called classic control environments in GEM and try playing with some of those, figure out where you have to make the substitutions and then see how it goes. All right, there's one other, someone asked about running more of a deep dive reinforcement learning sessions. And I do plan to do this. This is pretty much an intro to reinforcement learning with some things missing that I'd like to add and fine tune so that it fits better in a short time frame. There's a lot of more advanced material we can get into, and I do hope to start filling out that material. If you followed the the GitHub repo, you'll certainly get notified when we push updates, like more lessons. There's a couple that we have in process that we didn't have time to finish before this event today, and we will be scheduling ones periodically. I should say, if you go to the well, let me go back to it. If you go back to our events page, we are planning, I guess, I don't think we have it here. Yes, here it is. We are planning an online race summit this fall. We haven't quite got the details worked out yet. We're hoping to announce them within a week or two, but it'll be sometime in the September, October timeframe. Well, we'll have some tutorial sessions then ahead of time, and then 2 full days of talks about Ray, people using Ray in various ways, and some really exciting keynote speakers as well from the industry. So that's the plan for that, and we'll schedule periodic Academy sessions as well, besides the 2 that you see here. Actually, there's only 1 left that's right. That'll be next month. Any other questions before we break for the day? Maybe I'll leave it here. All right. I very much appreciate your time today. Someone also asked if we're hiring. We are, in fact, hiring. Let me go back to the top here. Oh, there it is, jobs. If you go to our jobs link, these descriptions are fairly open-ended because we're kind of just hiring across the organization, but definitely feel free to apply to any of these openings here. Otherwise, I very much appreciate your time today. Thanks for all of you who showed up, and I hope you enjoyed this. I hope you have some more fun with it. If you can, do play with the sessions this afternoon, and then about 3 o'clock, we'll have to turn them all off because they get kind of expensive after a while. I do appreciate your time, though. Thanks again.